Okay, so today we're going to look at what's called U substitution. And you can think of it as reversing the chain rule.
Oh, I just looked at it. It's like, do you?
And so we've actually kind of already done this, right? Because once you do this a bunch, you can do a lot of it in your head, right? Without actually having to formally do it. But we can formally do it as well, right? And we've done that with stuff like cos 2u. The integral of cos 2u. And you say, well, okay, what's the integral of that? And I've got that 2 there, but the chain rule says I'm going to have a 2 out front, so I have to multiply by half, right? So we've already kind of done it, right? We've been doing that kind of stuff. But if we get more complicated expressions, and we'll start off with actually one that's fairly simple, and you'll kind of see how this works. So let's say we want the integral of 15x squared times the cube root of 5x cubed plus 7 dx. So looking at that, what do you immediately notice?
You can take it off 15.
Well, I got a 15x squared, but what do you see? Yeah, it's like, hey, the thing under the root sign, that 5x cubed plus 7, its derivative is 15x squared, right? So I know that, when I'm taking the derivative of something like this, I'm going to get a 15x squared, right? So what we do is we say, we're going to let u stand for, so we're going to let u equal 5x cubed plus 7. Hence, u substitution, right? Then what's du? Or we could say du by dx is equal to 15x squared. And we'll write that in differential form. So you can sort of think, although this isn't really a fraction and you can't sort of really multiply, you can actually write du is 15x squared dx. Okay, so from now on, when we say u is this, we'll go straight to du is 15x squared dx. So if we look up here, we say, okay, the 15x squared and the dx, the stuff that's green, I can replace that with what? Du. And 5x cubed plus 7, I can replace that with u. So we can rewrite this, and I'll do this one time, right? So we can see that the green stuff is that. So we can rewrite this as the integral of the cube root of 5x cubed plus 7 times 15x squared dx. And now we can sort of say, wow, it's kind of obvious now. You can rewrite that, and you can put a u underneath the root sign, and you can put a du here. And then we will only be in terms of u and du. So it's the cube root of u du. Okay, and that's easy to do, right? So what's that equal to, right? That's u to the 1/3 du, which is equal to, so we know the inverse power rule, right? Because we're going to add 1 to this, which will give us u to the 4/3. And then we're going to multiply by the reciprocal of 4/3, which is 3/4, right? So we get 3/4 u cubed plus some constant c, right? Got to remember the c, general antiderivative. And then we resubstitute, right? So we go in and we say, well, hey, wait, the original question didn't have a u, but we know what u is. U is 5x cubed plus 7 to the 4/3 plus c. Okay, and then we're done. And if you take the derivative, what do? Well, 4/3 times 3/4 is 1. 5x cubed plus 7 to the 1/3, right, subtracting 1, times the derivative of 5x cubed, which is 15x squared, and boom, right, we got it. So that's the idea behind u substitution. right? Is we want to substitute. And when it works is this, right? If we're given something of the form, oh, let's go to a new page. Given something of the form, f of g of x, right? So again, there's that inner function, right? Times g prime of x. So we've got that inner function, and then we've got its derivative, right? The derivative is sitting out. That was the 15x squared, right? 5x cubed plus 7 and the 15x squared dx. Okay? Then that's equal to the integral of f of u du, where u is equal to g of x. Right? So we substitute u for the inner function, which allows us to then write it as a function of u du, and then that's integrable. That's a word, integrable. And then we're done, right? And then we substitute back at the end, right? Then we put in for the u, we then substitute back in the expression that we had for u, and there we go. We have the integral, right? And then we can check that by taking its derivative. Okay, so let's do a few more. The integral of 2 minus 1 over x times the sine of 2x minus ln x dx. So we look for the inner function, or we look at the thing that's easiest to integrate, right? Sine of 2x minus ln x is very easy to integrate, right? What's the integral of sine? Cos. So that's easy to integrate, right? So if we didn't have that 2x minus ln x, if we had the sine of u, that would be very easy to find the integral of. So that's what we do, right? We let the inner expression, also we look and we say, what's the derivative of 2x minus ln x? Oh, it's this. Okay, good. So now we know where we stand. So we let u equal 2x minus ln x, which means that du is 2 minus 1 over x dx. And we can see, okay, look, I've got the 2 minus 1 over x dx, and I've got the u. So it's the integral of sine u, that's that, and then what's this guy? Du. Now, it doesn't get much easier than that, right? I mean, what's that? So actually, it's negative cos u, right? Because the derivative of cos is minus sine. So negative cos u plus c, but u is, oh, wait a sec, sorry. What's u? Oh, yeah, 2x minus ln x. And we're done. Let's keep going. It's a turn. I'll give you a chance to go to coffee again. We'll pause. 5 times 6x plus 1 times e to the 3x squared plus x. Well, it's easy to integrate an e, right, an exponential, so that's the thing we want to integrate. We'll let u equal 3x squared plus x. So u is equal to 3x squared plus x. So du is 6x plus 1 dx. And we got a problem. Oh, two problems. One is that there's a dx on the end of that. So that solves problem number one. So the problem is I got 6x plus 1 dx. I can see that there. But I also got this 5. So how are we going to deal with that?
I thought to go outside the thing.
Well, so
Like the technical term.
see, what I really want to do is I want to replace 5 times 6x plus 1 dx with du, right? Like I've got this, but so we could say 5 du is equal to 5 times 6x plus 1 dx, which now says, hey, you can replace this, this, and this with 5 du, right? So we'll go the integral of, okay, so what do we got? 5 e to the u du, right? So we've replaced the 5, 6x plus 1 dx with 5 du.
Why can't we just leave it?
You can pull it out front now.
But I mean.
Oh, why didn't you do that in the
before-
first place?
Yeah.
I don't know, because then it wouldn't have made my examples. You're right, we should have just done that. Fine. Yeah, all right, I'll show you in the next one. So the derivative of e to the u is just e to the u, right? So we get 5 e to the u plus c, which is 5 e to the 3x squared, what was u? 3x squared plus x plus c. All right, fine. The next one we're going to have to do this for real. Yeah, okay. You didn't need to do that. Yeah, I guess. It's what happens when you don't calibrate. Okay, fine. So let's start off by rewriting this. Okay, so now what do you say? What's my u going to be? One minus 3x squared, right? We could very easily take the integral of something to the negative a half. It would be a lot easier if that something were just a single variable, right? So fine. So we say, let u equal 1 minus 3x squared. Then what's du? Are you positive? Negative 6x dx. So here's the problem. We have 3x dx, or we move the 3 out in front, and then we have x dx. But we need to have negative 6x dx. So what do I have to do to get a negative 6x dx? Times both by negative 2, right? So I can go negative 2 du is, where is that? Are we timesing by 2?
Yeah, we want.
We're not timesing by 2, are we? Divide by 2. So I want this to be negative 3x dx, right? And I'm going to replace that, so I've got, well, okay, so it's not negative. So how do we make the 3x dx?
Positive. We want to be positive.
I want to be positive, you're right. Okay.
Divide by negative 1.
Off the rails.
Okay, so if I multiply this side by negative a half, I'll get the 3, right, which I want, 3x, which means I have to multiply this by negative a half. Okay? So now we can replace 3x dx, right, by negative 1/2 du. So now we come down here. Okay, so we've got u to the negative 1/2, and we've got negative 1/2 du. So we can pull the negative 1/2 out front if we want. You could leave it. So really we could have put the negative 1/2. Well, I guess we can't just isolate it. So we could have written negative 1/2 u to the negative 1/2 du, or we can go negative 1/2 integral u to the negative 1/2 du. Okay, so any of these three is really an acceptable way to write the next line, right? So you can go any, you don't have to go one to the other to the other. You could just immediately go straight to this, or to this, or to that, depending on your preference. So what's the integral of u to the negative 1/2? what do? We gotta add 1 to get u to the 1/2. And then yeah, you divide by 1/2, right? Or multiply by 2. So we have negative 1/2 times 2u to the 1/2, which will just be negative u to the 1/2 plus c, but u is 1 minus 3x squared. To the 1/2. Okay, so you do the integral, or sorry, do the derivative of that, you'll get negative 1/2, 1 minus 3x squared to the negative 1/2, times negative 6x, so we got negative 1/2 times negative 6x, which is positive 3/2, and then we got this to the negative 1/2, right? Which is what we have here. Okay, so to check back, right, and the check back is make sure, hey, did I, because what did we first write? We had a 2 in here first, right? Okay, well, that would not have been right, so you can back check by just doing the derivative. Okay, so what if we have the integral of 3 over x ln x? What should u be? So if we do u as ln x, then the derivative of that is 1 over x. So that's good because we got an x on the bottom there, right? So we want that. Okay, and then we got a 3, but we'll take care of the 3. That's just a constant, so we'll deal with that. So u is equal to ln x. Du is equal to 1 over x dx. Okay, so this can be written, we can kind of split that up. Well, what do we need? So we've got like a 3 over x dx, so we need that to be a 3 over x. So we're going to multiply by 3, right? So 3 du is 3 over x dx. Okay, so we can split this out. 3 over x. Well, here, let's move that over a bit. So let's go 1 over ln x times 3 over x dx. Okay, so we can say, hey, we can replace that with 3 du. So put the 3 out front, right? So 3, 1 over u du. Okay. So this we replaced with 3 du, but we said you can move the 3, it's a constant, move it out front there. You could leave it there too, right? And write 3 over u. So this is just ln u. And when I say ln u, I of course mean the absolute value of u, right? And then that becomes, well, then the 3's here, so it's the same. You could do 3 over u, then that would be 3 ln u. Okay. I like to take constants out front, right? So 3 times the integral of. Remember that property, the one I didn't do yesterday in the video, but was on the sheet? You said you left the properties on. And then that's the absolute value of ln x plus c. Okay. Now you need that, right? So I mean, even though in the original, right, we know that x has to be greater than or equal to 0, right? But we know that ln of x could be negative, right? If you're doing the ln of like 1/2 or something, then that could be negative. So that's why we have to do this here, right? We take into account that, yeah, the ln can be negative, but you can't take the ln of a negative. So we do the absolute value. All right. Still yet more. Just a shower. They're going to shower down. Okay, what's u? Five x squared plus 4, right? Because then du is going to be 10x. We got a 3x. We just have to make the 3x into a 10x. We could do that by multiplying by a constant. Okay, so u is 5x squared plus 4. Du is 10x dx. So here's another way you can sort of think about it if you want. You could say, all right, I've got 3x over 5x squared plus 4. I need to get rid of the 3 and replace it with a 10. So we're going to multiply by 10 over 3. Right? That gets rid of the 3. We now have our 10x. But hey, you just changed the value, right? You multiply by 10 thirds. All right, so now I got to undo multiplying by 10 thirds by multiplying by 3 tenths. So what's 3 tenths times 10 thirds? 1. So now I'm not changing anything, right? I'm multiplying this by 1, but it's going to allow these guys make that a 10, and I'll take the 3 tenths out front. Okay? I can do the same thing up there, right? We could just say, hey, I want to have 3x dx, so I'm going to go 10 thirds times, or sorry, 3 tenths. I'm going to go 3 tenths times 10x dx. That'll give me my 3x, and then I got to go 3 tenths here as well, right? So kind of the same deal, right? Just this is happening in here, and this is happening over here. So it depends on your preference, right? So you just say, all right, so let's take the 3 tenths out, and now this is just 10x, don't forget the dx, dx and 5x squared plus 4, so it's 3 tenths. Okay, so what do we got? We've got 1 over u, right? That's on the bottom, the u, and we got 10x dx up top here, that's du. So we got 1 over u du, and the integral of 1 over u is the ln of the absolute value of u, plus some arbitrary constant. And u, we know u. And 5x squared plus 4 is always positive anyways, right? Okay, so that's part 1. Part 2, we can also evaluate definite integrals, right? So remember, an indefinite integral is a function of x. A definite integral is a number, which may or may not be the area under the curve, right? If the curve is totally above the axis, then it's the area under the curve. Otherwise, it's the sum of the area above and below. So, from -2 to 0, 2x squared root 1 minus 4x squared dx. So what this says is x equals -2 to x equals 0, right, of this. But we're going to get rid of the x. What are we going to make the x into? Or, sorry, what's the u substitution? So u is equal to, okay, wait, sorry, this is a cube. Otherwise, there's bigger problems. So u is 1 minus 4x cubed, which makes du equal to -4x squared dx. -12x squared, -12x squared dx. And we've got a positive 2x squared dx. So if I want to make this into a positive 2, what do? Divide by -6, right? Or multiply by -1/6. So now the 2x squared dx that's up there can be replaced with -1/6 u. Or sorry, -1/6 du. And the root of 1 minus 4x, whatever that is, can be replaced with u. But we have the bounds of integration, right? They say x is -2 to x is 0. So we got to say, okay, wait, we need one more step. When x equals -2, what's u equal to? Well, we got a formula, right? U is equal to 1 minus 4 times -2 cubed, which is 1, -2, -8, -32, minus -32, 33. And when x equals 0,
It's 1 minus 32 is -31.
well, it's -32. So -8. 4 times -32, 1 minus -32. Yeah, watch your minus sign. U is equal to, well, that's pretty easy, that's just 1, right? So if we're going to do U substitution, we also have to substitute for the boundaries of the integration, right? Which is now U. So this is U, well, negative 1/6, right? We got the negative 1/6. U going from 33, that's our lower bound, to 1, that's our upper bound, of the square root of U du. Okay, so that's U to the half. Add 1, we get 3/2, multiplied by the reciprocal of 3/2 is 2/3. So that's 2/3 U to the 3/2. And we want to evaluate that from a lower bound of 33 to an upper bound of 1. All right, so negative 1/6 times 2/3. We've got a 1 and a 3, so we get negative 1/9. And we get U to the 3/2, going from 1, upper bound of 1 to a lower bound of 33. Now I have two choices, right? I mean, I could have just put the negative 1/9 here and gone negative 1/9 times, or I can leave it out front and then evaluate. So I've chosen to leave it out front. So the upper bound is 1, and the lower bound is 33. All right, so we have negative 1/9. Still back this up. So 1 to the 3/2 is just 1. Minus 33 to the 3/2. Okay, 33 to the 3/2. Which point here we go over here. 33 to the 3/2 is the square root of 33 cubed, which is equal to what? You change from entire radical to mixed radical. So it's 33 root 33, right? Because we've got a perfect square, right? We got the 33 cubed, so that's 33 squared. That can come out of the square root sign as a 33, and then we're left with the root 33, right? All the way back to, what was that, radicals in Math 10C. Now, it's kind of bad form to lead with a negative if you don't have to. Okay, so we can do that. So we've got 33 to the 3/2, which becomes 33 root 33. And then we got that negative out front, so we'll make it positive, flip the signs in the brackets, and away we go. Ask not for whom the bell tolls.
It's not supposed to say 33 root 3. There's a right? 33 root 33.
Yeah, did that twice. Just the bike on Kijiji, guys. It's still for sale. Lol. What? All right. Let's do another one. So it's another definite integral. We definitely have to do some definite integrals.
Is this the last one?
No, one more after this.
Oh.
Definitely only one more. Then we'll go do our survey, and then you can come back up. And they say the survey, what do they say? Take about 25 minutes.
What? Can I not do it?
No, look, it won't take you 25. I can almost guarantee.
Is it optional or?
No. What are we gonna make u?
You're not even gonna know if
X
it's
squared.
No, x squared, right?
Take the offer.
Go ahead.
Take it.
$500. Let's meet at YG.
Still on sale.
X squared. Oh, now do I write it tonight? What if I crash my means? That would be bad. So what's du? 2x dx. What's the adjustment we have to make? Okay, so we need an x dx. We got a 2x dx multiplied by half, right? Both sides. Okay, so what do we do with the half? We stick it up front. Oh, but wait, we can't do that yet.
Not yet.
These are x's, right? So what's u? So when, we can do this over here. When x equals the square root of pi over 2, what's u? Just pi over 2, right? We're squaring it. And when x equals the root of 3 pi over 2, and u is 3 pi over 2. So we always have to adjust, right? I mean, you have a choice, right? The choice is in here. That wasn't a definite one. Oh yeah, this was a definite one. So in here, when you got to this point, you could have substituted back for the u. You could have put in the 1 minus 4x cubed, right, down here. And then you would have kept your original bounds of integration because now you would be dealing with x's. It's just a lot easier not to do it that way, right? I mean, why substitute? If it's a definite integral, we know we're going to get a number. So let's go with the easy one. The easy one is just working with the u, right? The hard part is just we've got to make sure that our boundaries are in terms of u and not in terms of x.
Yeah.
Okay? Otherwise, you can leave your boundaries in terms of x, then you've got to change it back to x and, the y. So this will be pi over 2 to 3 pi over 2. We got that half, so let's throw the half out front here. We've got the cos x squared, but what x squared is that? So it's cosine of u du. And what's the integral of cosine? Sine. So it's sine u, well, it's 1/2. Sine u evaluated from pi over 2, well, actually, sorry, 3 pi over 2 to pi over 2, right? Let's start with the upper bound. So it's upper bound minus lower bound. All right, what's the sine of 3 pi over 2? Sine curve. -1. Minus, what's the sine of pi over 2? 1. And this works out to -1. Okay, one more. Don't go to the survey. Be excited. It's your chance, right? It's your chance to get feedback to say, man, I wish that you'd have done this.
I wish I had.
Or that. Yeah. You're improving it. Some of you may have younger siblings. You say, oh, it'd be so much easier. Okay, so this integral is easy, right? We don't need to do anything special with the e to the x. This integral, not as easy. We do have to do something with it. So we can split this up, right? We know from the properties of integrals that this is equal to the integral from 0 to 1/2 of e to the x plus the integral from 0 to 1/2 of 2 cos pi x dx dx. We don't have to do any substitution here, right? That's straightforward. We do have to do substitution here, or we're going to do substitution here, right? So what are we going to substitute? Well, so u is pi x. Then what's du? Yeah, du is equal to pi dx. Now, we don't have a pi dx. We got a 2 dx. So how do we make pi dx into 2 dx? Multiply by 2 over pi, right? So 2 over pi du will be equal to 2 dx. Now 2 over pi is a constant, right? So that's good. We'll just pull it out front. But wait a sec. We don't want to touch the bounds of integration here because we're just leaving this as x, right? We know the integral of e to the x, so that's easy. But we do have to change the bounds of integration here, right? So when x equals 0, what's u? That's pretty easy, pi x, so that's 0. And when x equals 1/2, u is pi over 2. Okay, so let's go over here. What does this become? Becomes the integral from 0 to 1/2 of e to the x dx. Okay, we're not going to touch that one because that's easy. Plus the integral from, okay, now we're going to be in terms of u, so 0 to pi over 2 of, oh wait, we got that constant up front, so let's move this over a titch. So what was the constant I need? 2 over pi. So 2 over pi, the integral from 0 to pi over 2 of, okay, now, that 2 dx, that was replaced by the 2 over pi du, so we've just got cos u du. Okay, now we can do the integrals. What's the integral of e to the x? E to the x. Evaluated from 1/2 to 0, plus 2 over pi, and the integral of cos u, sine u, evaluated from 0 to pi over 2. Right. We don't have to add a constant here because we're doing the definite integral. And if you did, you just add it and subtract it, so you don't do it. Okay, so now we can evaluate. We'll get e to the 1/2 minus e to the 0 plus 2 over pi, let's do it this way, sine pi over 2 minus 2 over pi sine 0. Okay, so I've distributed the 2 over pi into the, instead of putting that in brackets. Sine of pi over 2, 1. Sine of 0, 0. So that's gone. So what do we got?
How come you only substituted in the pi over 2 and 0 from the integrals for the sine, not the e to the x?
So we're doing two separate integrals here, right? So when you look at the original, you say, that's easy to do, right? I mean, I find the integral of e to the x. I don't need anything special. That's a little bit tougher. So then we said, all right, you know what? There's a property of integrals that says the integral of a sum is equal to the sum of the individual integrals. So we're going to split this up. We're not doing anything with this. There's no u substitution needed here. Here, I got that pi x. I want to get rid of that. Okay, so we do this. Now that changes our bounds of integration here, right? So now we can't go from 0 to 1/2. That's for x. We have to go from 0 to pi over 2. That's for u. So we do that here, right? So these are still 0 to 1/2. This is 0 to pi over 2. The 2 dx has been replaced with 2 over pi du. And we just said, look, 2 over pi is a constant. We'll put it out there. So there's the 2 over pi du. That's my 2x dx. Yeah. And so we get e to the 1/2. What's e to the 0? 1 plus 2 over pi. Okay. Done.